So today we're going to take a look at this idea of using a definite integral and substitution. So basically what you're going to notice changes when we go from the x to a u is that we have to update the bounds. So basically, if you want to look at this, you got to think about changing your bounds into terms of the new variable. And it's fine if at the end of all of this you decided that, maybe I'll just do the example and I'll show you, but this actually makes life easier, so you could choose to ignore this and go through it the longer way, but I think you'll see what I mean if we try an example. So let's say we were to tackle this question like we did before. We'd start by making a substitution. Maybe first of all we'd put a half out front and a 2 inside. Okay. And we'd probably say let u equal x squared plus 1, and du is 2x dx. Now that would have been fine. We could go ahead and make our substitutions, but the problem now is we have bounds to deal with. This integral used to be in terms of x, and the bounds with respect to x were from 0 to 1. So if the bounds with respect to x are from 0 to 1, we can't substitute until we also take care of the bounds now, this time in terms of u. So any guesses on how we could do that? Take a wild guess, anybody? Yeah? Sorry? Square it and add 1. Yeah, that's the relationship between u and x, is to square it and add 1. So the new lower bound is going to be stick in x equals 0, and I get 1. Stick in x equals 1, the upper bound is going to be 1 squared plus 1, which is 2. So now I can rewrite this integral in terms of u. It'll be the integral, this time, it goes from 1 to 2. It does not go from 0 to 1 anymore because I've changed the variable. It's going to be u cubed du. And the reason there's that advantage is now when you look at the antiderivative, there's a half out front here. Actually, that looks like a 24. Let me try to do a better job of that. That'll be a 1/2 u to the 4 over 4, and we're evaluating it from 1 to 2. So, I guess I might as well write it like this: u to the 4 over 8 from 1 to 2. There's nothing wrong with, if you were to say, okay, I don't remember what I'm supposed to do when it comes to substitution and the bounds, we could then put in the values for x back for u, make u equal x squared plus 1, and then use the original bounds because we put everything back in terms of x. But look at how simple this is going to be to evaluate. Like, that was the purpose in the first place, is usually we made a substitution to make the integral easier. So it's going to be easier to keep the bounds in terms of the new one. So I can probably do this in my head here. Well, let's see, I've been known to make the odd careless mistake, but that'll be, at 2 I'd get 16 over 4, or over 8, take away 1 over 8. So I'd end up with 15 over 8. And we can verify that in the original expression. So we'll just take a second here to verify it in the graphing calculator to see that it does, in fact, come out with this original integral. Okay, so we'll try that. So in the TI-83, I'll just put this part of it up as we did the calc, and there's an integral f of x dx, and what we got from that was 1.875, which in fact is the same thing as this here. So even though we've changed the bounds and we changed the variable, as long as we do this carefully and properly, we'll still end up with the same answer. Okay, so I'm going to have you try the second one, the next couple, using this idea of when you substitute, you're going to have to also change the bounds. Okay, so try this first one and then we'll recap. I don't know why it does this, but the bounds don't show up properly with this math software. This should be a 1 if it's hard to see, and this should be a 5. So I apologize if it's hard to read, but it should be a 1 and a 5. So I'm starting to lose space here. I'm going to put a new slide up, but I'll just rewrite it here so we can see it better. It's from 1 to 5, and let's just see what, so x over root 2x minus 1. Okay, so again, if we do this like we've been practicing, most likely this is what we'd be working on. And that x equals u plus 1 over 2. So I'm going to need all those bits of information to help me substitute properly. I also need to adjust these bounds here. So first of all, let's start with the lower bound. The new lower bound is going to be 2 times 1 minus 1. So it's still the same as it was before at 1. The upper bound is going to be 2 times 5 minus 1, which means it's now going to be 9. Okay. So in the new integral, I'm going to be going from 1 to 9 of x over root u, and I've got 1/2 du here. So I need to make a couple substitutions and try to rearrange this. So I'll bring the half out front. So 1 to 9. X, I've got a substitution here for x. So let's put that in. So that'll be u plus 1 over 2 times 1 over root u du. And probably the nicest I'm going to get before I have to start doing the actual integral, we'll take that out and get 1/4. So I'll have u plus 1 over root u. And in this situation, I'll make use of that monomial, and I'll use my exponent laws. So let's see here. That means I'm going to have 1/4 the integral from 1 to 9 of u over root u plus 1 over root u du. So I can write these now as exponents, and that'll be the easiest way to take the derivative, or sorry, the antiderivative. So it'll be u to the 1/2 plus u to the negative 1/2. And I can use the power rule in reverse. So I should end up with 1/4 2/3 u to the 3/2 plus 2u to the 1/2, and we'll be going from 1 to 9. Can I just double check? Did anybody else come close to this, or am I on the right track? Yeah? Okay. So at this point, I mean, it is possible, I think, to do this without a calculator, because you'll be taking the square roots. Right? These are square roots, and you've got perfect squares like 1 and 9. So it'll probably work out, but let's use the calculator anyways. So I get 16 over 3 for this integral, or 5.3 repeating. So just hands up, how did we do there? Did we were able to do the substitutions, change our bounds okay? No. Just okay, well, we're going to keep practicing, but can I see where are we at right now? Okay, about half of us possibly. So let's try, again, similar to like last day, you're going to be making a substitution here, but don't forget to change your bounds when you do. So I think I'm still going to do this one on a new slide just to make sure it's not too messy. So the integral this time is from 0 to root 2 of x e to the negative x squared over 2. So the substitution, if you're looking at the pieces, this one here, if I was to take its derivative, it's going to be pretty close to that piece. So that gives me some hint that I want to make u equal to negative x squared over 2. The other hint, of course, is that if it was just a simple e to the x, it'd be an easy integral to do. So that would also help reduce how complicated the problem is. That leaves me with du equal to negative x dx. So I'm going to be missing a piece. I need a negative here, so I'll put one in the front and one there to make up for this negative that I need for the du substitution. The lower bound is going to be the negative of 0 squared over 2. So that'll be 0. And the upper bound is going to be the negative of root 2 squared over 2. So it's going to go to negative 1. So if I make my substitutions here, that's the integral I should end up with after I've replaced them, and the bounds should now be from 0 to negative 1. Okay, even though negative 1 comes before 0, where it came from is what you're replacing. So if it came from the top or the upper bound, it's going to replace the top position or the upper bound. Okay, even though you might see the numbers switch, don't overthink it. It just replaces wherever it came from. Okay, so this one, that will be a negative e to the u from 0 to negative 1. So that'll be negative e to the negative 1, take away negative e to the 0. So that's going to be negative 1 over e plus 1. And again, I think the math gets easier to do after that substitution, so it is nice to do it in that sense and change your bounds and use the simpler version. Wrap here. Okay, so here's the last one. Again, if it's hard to see the bounds, it goes from 1 to 5. All right, so I'll try to catch up here. You guys have a sizable head start. So we're going from 1 to 5 this time of x squared root x minus 1 dx. And just double check. Okay. And I'd probably make this substitution, which means my differential is going to be equal to dx. My bounds, lower bound is going to be 1 minus 1, will now be 0. My upper bound is going to be 5 minus 1, so it'll now be at 4. So the substitutions that I can make right now is to go from 0 to 4, x squared root u du, and this x squared that's left over, I'm going to have to make the substitution this way. I'll use this relationship to say x must equal u plus 1, so I can make the replacement here. And now it's all u in my integral. I don't have two variables, I just have the one. It's all u, yeah. Okay, so I would expand this. It's only a squared. It's not that bad to deal with, so it would be u squared plus 2u plus 1 root u du. And I'm just going to jump to another. Then I distribute it. So if I got 2.5, that'll be 5 out of 2. Um, 1.5 will be 3 halves. And 1, so that'll just be what it was before. So that'll be u to the 1/2. So at this point, I'm ready to just use the power rule and integrate them. So it's going to be 2 out of 7 u to the 7 halves plus 4 out of 3 u, sorry, should be 4 out of 5. 4 out of 5 u to the 5 halves plus 2/3 u to the 3 halves. And I'm going from 0 to 4. Now this will work out as it won't be that bad of a number, because the square roots we're dealing with here, these square roots, I can handle that for 4 and 0, but it's going to get tough to do without a calculator. Like for example, the 7th exponent, you may not know that it's 128, right? You may not have that level of nerdiness yet, but it's also going to be a fairly large common denominator because you got these 3 prime numbers. I believe that's going to make is that going to be 105? So let's just use the calculator to find this number. Okay, so as a decimal, I get a number that's 67.50. We'll truncate it here. But as a fraction, it would have been, that would be the exact value if you were looking for it as a fraction. Okay. So that's as far as we're going to talk when it comes to substituting for a definite integral. But I do want to, there was a couple properties that we hadn't discussed yet. And that's what the next picture is for us to talk about. Let me zoom in a bit. So this next picture, I'm going to split this. I mean, we could just go ahead and do this. It's not that difficult of an integral, but what I want to do is I want to show you guys a couple of properties. So first of all, if we're looking at this, I'm going to separate it into 2 pieces. So we're going to take the integral from 0 to pi of sine x plus the integral from 0 to pi of cosine 2x. And I'm going to show you a couple of properties that we have. So for example, what I want to start by doing is I want to start by looking at this one here, cosine 2x. And let's take a picture of this. If I was to look at this graph, if you remember, this is going to have a period of 2 pi divided by 2, which is pi. So this is going to be one full period from 0 to pi of a cosine graph. So here's what it would look like. So can anyone, does anybody remember anything about this cosine graph that might help you answer this question in terms of area and integrals? Yeah, why do they cancel out? Yeah, so the amount of area that we would have under here is going to be the same as the area above. There's a special, do you know why that, do you remember the special property? It starts with an S, if that helps.
Special property?
Special property, no.
Super property?
It was actually symmetry, right? It was symmetry that was what helped us figure this out. So because it's a symmetric, the symmetry that it has over the x-axis, that's how we can say that we know this is the same amount, that those 2 black areas is the same as the purple area. So there's going to be nothing contributed here from that graph. The other picture here that I wanted us to look at was, it may be advantageous for us to look at a graph and say, okay, instead of doing the whole thing, maybe it's easier for us to say, let's look at the picture. The area in here, because of these symmetries, should be equal to the area under here. So another way we could have approached this problem from the beginning would be to write this as the integral from 0 to pi over 2, exactly halfway where we were here, but double the amount of area that we found for sine x plus cosine 2x. And then, I guess we might as well finish off by answering this question. So all we were left with was this piece here, which was 0 to pi of sine. So that's going to be the negative cos from 0 to pi, which is going to be the negative. Cosine of pi, refresher, do we remember this? Cosine of pi? Yeah, it's -1. And then we're going to take away, what's the cosine of 0?
1.
Yeah, it's 1. So it's going to be +1 plus 1. It ends up being that the area in that figure is 2. Okay. So the black plus the green area would equal 2. I'm not sure just how much you're going to see that being used in your homework tonight, but the symmetries that show up there it's a good property to know about.